This is the 6th of 7 parts in our DC Design Guide, and I'm your presenter, Ian McCluskey. Inverters, here we go. As promised in the load analysis section, we are revisiting our load sheet here. So pull it out. This time, we are just looking for the instantaneous power draw of each load, so the calculations are less complex. However, we can't underestimate the importance of apparent power in volt amps, used to determine the load's power factor, which is the ratio of real power, watts, used to do work, over the apparent power in volt amps actually supplied to the circuit. It is always between 0 and 1, and usually shown on the appliance specifications if relevant. Now, without getting too into it, apparent power is a relatively complex topic and may be important to Google and read a little bit about before proceeding, if you're interested. Otherwise, go ahead. The inverter must be able to output enough power to cover all backup loads at peak usage. So the surge load is also key to inverter sizing. Surge load is also known as inrush current, which is the max instantaneous power drawn by a given load when it turns on. It is most significant in motor-driven loads, for example, pumps. Let's identify the max continuous apparent power our inverter will have to supply in any case. Multiply the load's quantity and watt rating, then divide by the load's power factor. Next, find the sum of the resulting volt amps for each load. For example, compact fluorescent lights, if you have 10 and they're each rated 10 watts, that would equal 100 watts. However, CFL lights tend to have a low power factor. In this case, 0.3 is the example. So 100 watts divided by 0.3 is equal to 333.33 watts. As you can see, power factor can have a large effect on our inverter sizing. We will now find the surge watts to add to the total apparent power. We usually see surge ratings on loads with motors, such as air conditioners, refrigerators, power tools, among others. The surge load is the quantity of a given load times the watts of that given load times the given surge factor. It should be apparent on the appliance spec sheet, or you can look up a typical surge load for the load. Then take the sum of each surge watt. For example, say a 300 watt refrigerator, if there's one, would be 1 times 300 watts times a surge factor of 2, average for refrigerators, is a 600 watt surge. This is in addition to its base load. Some loads will have a surge rating in watts instead of a surge factor. In that case, just multiply the surge watts by the quantity. Now that we have the total load volt amps and the total surge watts, we can verify the inverter we want is going to work, or use the numbers to pick a better inverter for the application. Is the AC total load volt amps, apparent power, less than the inverter minimum continuous volt amp output rating? You'll notice on inverter spec sheets, the output rating is actually given in volt amps because they know apparent power is more important than real power in this case. Is the AC load total volt amps plus the total surge watts less than or equal to the inverter 5-second surge rating? Even if these statements are true, there is one last thing to check. Make sure to check that the charge controller's max output is not higher than the inverter's lowest continuous volt amp rating in order to protect the inverter. Also, confirm the inverter operates at the selected battery voltage, AC output voltage for the grid, and grid frequency. In the US, of course, this is typically going to be 122/40 split phase for a residential project and 60 Hz frequency. All right, you're almost there. There's only one video left.